Here's a question. How do we know when something is horizontal? And I encourage you to pause the video and think about that, but I'll explain it anyway right now. One of the answers to this question is if this something is parallel to the surface of water, of still water. And what do I mean by that? Well, if you take a bottle of water, then you know that no matter how you orient it, and I encourage you to try that on your own right now, with the water inside of it, it'll always orient itself in the bottle to be exactly horizontal. And so that's a property of physics, and that's a question you might have heard in a physics class when talking about something called operational definitions, which just encourage us to think about the world around us in simple ways. And that's exactly what we're going to do in calculus when we're going to talk about this current subject of maxima and minima. And so the purpose of this video is going to be setting up some ground rules and housekeeping for our first real applications of derivatives in analyzing functions and their behaviors. And so the whole point of this exercise here was so that you can test your intuition and test the flexibility of your mind before we go into explaining the concepts of the video. And so I encourage you at the same time to think about how do we know when something is perfectly vertical? So that's an interesting question to ask. So anyways, let's get on with it. Let's talk about maxima and minima. Now you probably know what this means already, but if you have a graph of a function, something like this maybe, then there's obviously got to be some point where it's the greatest value and a point where it's the least value. And those are called maxima and minima respectively. And together they're called extrema, all right, extreme points. And so the idea there is that in a lot of applications in statistics or economics or optimization, which you have done in Algebra 2 and trigonometry honors classes or regular classes, you want to know sometimes what's the best way to, and what's the best outcome of a certain situation. And that could involve the greatest value of a graph or of a function that you don't know the graph to. And so you have to use math to figure that out, to optimize the maxima and the minima. So let's set up some ground rules. So let's define, first of all, what a relative maximum and a minimum are. So relative maximum or minimum mean that if any interval around some point m, which I'll write right here, so here's our point m, and if we have any interval around it, so we have a little bit of a nudge to the left called delta, a little nudge to the right called delta, and any interval within that value of m and around it, if the function evaluated at m is the largest value of any value of x within that interval, we call it the relative maximum. So in this example here, m is a relative maximum. But if we take another point, let's call it the m2, so we have m1 and m2, over here, if we take a little nudge to the right and call it delta, and a little nudge to the left and call it delta, then in this interval, if that point m2 evaluated, when you have f evaluated at m2, if that's the smallest point of all the possible x values evaluated within the interval, then we call m2 the point at which the function f has a relative minimum. And that seems to make sense with this example over here. So you might also notice now with your intuition a special property about maxima and minima, or at least relative ones for now. You might notice that the points where they occur also seem to have horizontal tangents. Okay? And so what does that mean? You'd be exactly correct. And so we define a critical point of f, or I'll call it c. C is a critical point, or as I'll call it on its own, just a critical. All right? It's a critical if there's a horizontal tangent at that point. That is, if f prime of c is equal to 0. And that's the case. If a function has a critical point c, if its derivative evaluated at c is equal to 0. So as you can see here, the f prime of m1 and f prime of m2 are both 0. But is that the only case when that's happening? And I'll tell you right now, it is not. And I encourage you to think of a friend that is our best friend whenever we want to provide any counterexample of any kind, the absolute value of x. And with absolute value of x, that's actually a horrible drawing. I'm going to try and redraw that. Here we go. Let's see. There you go. It's a bit better. We can see that there's clearly a minimum with the definition that we've used of any interval around that point 0 here. This is absolute value of x at 0 is the least value. But we take the derivative, we know that that's actually not differentiable. So we have absolute value of x over x, and we have the 1 and negative 1 lines here. And at 0, there's no value. It's not defined. Which also motivates the fact that a point c is also critical, not just if it's f prime of c is equal to 0, but also if f is not differentiable at that point c. Like the case with absolute value. There's clearly a minimum involved, but it's not differentiable. Okay, so we have relative extrema now at point c, where c is a critical point. And so that motivates the property that if f has a relative extremum at c, then C has to be a critical point. And I encourage you to try and prove this on your own with the definitions we've provided. But we also want to think about the contrapositive of that statement, where if C is not a critical point, then there's no extremum of f at C. And that's also true. So take a look at this. If we draw a function that looks like, let's just say like this, all right? If we take this point C over here, it's not an extremum because in any interval around that point, there's always some value greater or less than it in any interval, no matter how small or how big, okay? And that also means that it's also not a critical. As you can see, this function looks like it has a derivative here, which is the slope of the tangent line, which is not 0, all right? It looks like it's negative. So that's kind of proof of the contrapositive statement. But this is only about local minima and maxima. And let's be a bit more like Mr. Worldwide and go global. So we're going to take a look at global or absolute maxima and minima. So absolute maxima and minima, or max-min, I'm going to say. So what is this, and what's the difference between them? So I'm going to formally define it. If I is some interval, okay, within the domain of a function f, where the point m, all right, a point m is within that interval I, so m is an element of I, okay, then the function f has an absolute or global maximum at m if the value of the function evaluated at m is greater than or equal to f of x for any point x within that interval, okay? And likewise, the function has a global minimum at m if the value of f at m is less than or equal to f of x for all x's in the set of I, in the interval. So that's pretty wordy, so we're going to provide some examples here. If I take the function e to the x, and I take it on the interval, let's say 0 to 1, like this. As you can see over here, it doesn't have any derivatives that are equal to 0, all right? And so we can't really tell right away if there's any maximum or minima. There's certainly no relative maxes or mins here, but on the interval of 0 to 1, there are points where that function evaluated at those points is less than or equal to and greater than or equal to for all those values within that interval I. So here our interval I is going to be equal to 0, 1. And you can tell right away that since this function seems to be going from only getting greater in value, that the smallest value in this interval is going to be at 0, which means that's the global minimum or the absolute minimum of our interval. So we have absolute minimum, 0. And then 1 seems to be the greatest value, and so that's going to be the absolute maximum. And yet their derivatives are not equal to 0 at those points. So that's an important thing to know. That's the really important distinction between the global and relative max or min. That you won't always have those situations where the derivatives are equal to 0. Okay? So that's really important. You could have them equal to 0. So let's take a look at that example, where if you have an interval like this, let's just say like this, and you take the interval from here to here, all right? The smallest value seems to be right over here. It's not an endpoint. The derivative is equal to 0, and the derivative here should also equal 0, and this tangent line has a horizontal tangent. So it is possible for relative minima to also be the absolute minima, and relative maxima to be absolute maxima. Okay, let's give another example. Let's say we have f of x is equal to the function root of x, okay, the square root of x, on an interval I, which is going to be the closed interval containing all the points between 0 and 25. Okay? And let's graph that real quick. So, we know what the root of x looks like. It looks something like this. And we have 0, 1, 2, 3, 4, 5, all the way to 25, like over here. All right, I'm going to extend that graph a bit more, or like this. So we know what it's equal to at 25. We know it's going to be 5. So at this point here, it should be 5. At 0, we know it's 0. And in this example again, we see that the absolute minimum is going to be at 0, and the absolute maximum is going to be at 25. Because this function is greatest in this interval at 25, and it's least at 0. So I hope this example is a bit more helpful. But now I feel like doing some gambling, all right? I'll give you $1 million, or even I'll give you even $1 billion, okay? I swear. If you can find me a continuous function on some closed interval I, all right, some closed interval that has no maximum or minimum on that interval, all right? And I'll pause this. You can pause this video to think about that and try and win your $1 billion. And you can search your whole life. But honestly, in my opinion, you're better off trying to earn $1 million from Bitcoin, because the extreme value theorem, as we're going to call it, extreme value theorem guarantees that you can always find a maximum or minimum, and in fact a maximum and a minimum on any interval. All right, so it's extreme value theorem. I'm going to write it out like this. It's also called the EVT, like this. And so again, it tells you that for any function that's continuous and defined on some sort of closed interval, all right, you can always find an absolute maximum or minimum. So let me give you an example here. Let's draw this function like this. All right, this little snippet here of some function that may do a bunch of other crazy stuff later. All right, we're just focused on this interval right over here. This is a closed interval I. All right, so this is our interval I. I'm going to label it. We can see here, obviously, that there are both an absolute maximum and minimum. What about a function that's what we call strictly increasing, all right? Something like this on this interval. Well, even here, we see that if we isolate this interval I, we see that there's an absolute minimum right over here and an absolute maximum over here. So you can also zoom in infinitely small, like right over here in this interval. There's going to be a minimum right over here, a maximum over here. So I encourage you to draw out any function or any curve that's continuous on a certain interval, and I encourage you to yourself try and find out that no matter how small your interval is, you'll always have a point that's the greatest and a point that's the least. And that goes back to the idea of the beginning of the video, of the intuition. There's always going to be a point that's greatest and always a point that's least. But what about a case of a constant function, such as y equals 2, all right? Every value is the same. So how do you account for that? Well, remember the definition of the global or absolute maximum and minima. It tells you that a function at that point m has to be less than or equal to all other points in the interval, or greater than or equal to all the other points in the interval. And in that case, in the constant function case, every point is both a maximum and a minimum in that way. So you cannot break the extreme value theorem there either. All right. Now, the absolute extrema that we've seen before, they don't have to be critical points, as we've said. They could just be the endpoints here. But if the absolute extrema happen within an open interval, like this one over here, where the endpoints are not taken into consideration, then they must be critical points. And so what do I mean by that? Let's draw that again. So if I draw out a function that's going to have a closed interval like this, okay, then we can see that here we have points that are the absolute maxima and minima that are not the endpoints of the interval. And so they have to be critical points because their derivative there is 0. And I encourage you to also convince yourself that this is true. The fact that if the absolute extrema occur within an open interval of a function, then they have to be critical points. Okay, and here's to take a look at that in action. If a function f is continuous on a certain interval that's closed, a, b, so I'm going to write a over here and b over here, and let's say that both a and b are zeros, okay, solutions to the function. So maybe it does something like this, okay? Then you might see what's going to happen next. If the function is both continuous on the closed interval ab and differentiable on the open interval ab, all right, then if the endpoints of both zeros are both zeros, so endpoints a and b are both zeros, then at least one point in between within that interval has to be a critical. And as you can see in this example, that's true. And I encourage you to draw a bunch of different random functions that cross 0 at some point, and more than once perhaps, and that you can guarantee yourself that there's always at least one point in between that has a horizontal tangent. Like in this case you have 2, in this case you have 1, all right? And so let's give another example, because we love examples. Let's do the function sine of x, that looks like this. As you can see, on the interval between 0 and pi, where they're both zeros, there's one maximum, and we know that that happens at pi over 2. On the interval between pi and 2 pi, there's one minimum, and that happens, of course, at 3 pi over 2. On the total interval, that the endpoints are not the maxima or minima, the absolute maxima or minima. Instead, the absolute maximum is still at pi over 2, and it is a critical, and the absolute minimum is at 3 pi over 2, which is both the relative and absolute minimum. And this is an example of something called Rolle's theorem, okay? Rolle's theorem, where the conditions we specified above of the endpoints of an interval both having 0 as the function evaluated at them, so the function starts at one endpoint being 0, ends at the other endpoint being 0, and guaranteeing that there's at least one point within there that has a horizontal tangent, that's what Rolle's theorem says, okay? And this is a special case of the Rolls-Royce of calculus theorems, called the mean value theorem. So I'm going to write that out, mean value theorem. Now, don't worry, because we have not gotten to the Ferrari, Bugatti, Lamborghini theorems of the Bugattis of calculus theorems yet. They are still to come. So don't worry about that. So we have the mean value theorem here, and what it states is very similar to what Rolle's theorem is. And in fact, if you turn your head when you draw out these horizontal tangents, you're going to get the mean value theorem. What do I mean? So let's draw a function again. It has the same conditions as Rolle's theorem, where a function has to be both continuous on the closed interval a,b and differentiable on that open interval between a and b. All right? Then what it says is that there exists at least one point c within this open interval, all right, within the open interval ab, where the derivative of that function evaluated at c, so the tangent at some point has a slope of f prime of c, okay, where that line is parallel to some secant line between those 2 points. So written out algebraically, this is f prime of c is equal to f of b minus f of a over b minus a. And again, this is true for an interval no matter how small. So in this case, we have a and b like this. We can connect these together. And as you can see in this example here, we can estimate 2 points c where this happens. So maybe there's like a one right over here. Oh, I don't know what happened there. Like this. Okay. Maybe we have a little horizontal tangent over here. Or not horizontal tangent, but a tangent parallel to the secant over here. And maybe somewhere over here. Okay? And so you can see the mean value theorem in action here. And if you turn your head or turn this entire graph so that this secant line from A to B becomes the x-axis, you're going to see that these become horizontal tangents. And that is where you have Rolle's theorem. And that's how Rolle's theorem is basically a kind of a result that comes from the mean value theorem. Okay? That's a really powerful result, and you're going to see the mean value theorem a lot in calculus, and that's going to be something that you really are going to want to hold on to. So I hope that this gave you a general idea of the ground rules and housekeeping of what maxima and minima are, and how they're going to be used, and how we're going to use derivatives to identify maxima and minima. Now, next up, we're going to see how derivatives of more kinds and higher derivatives tell us more about the function's behavior. Till next time.